Hi. In the previous video, we've learned how to deal with higher order differential equations. So basically, we learned how to find complementary function and a particular integral for a differential equation of any degree of any order with constant coefficients and constant term. However, we also learned how to deal with cases of variable term through the methods of undetermined coefficients. However, we notice one problematic thing. Every time when we have high degree differential equation, that high order differential equation, we will be dealing with characteristic equation of high degree. And this makes solving this characteristic equation extremely difficult. However, in various cases, we are not interested in the actual shape and form of the complementary function. All we want to know whether our particular integral, so equilibrium solution, is dynamically stable or not. And if we encounter complicated case like this, we can always resort to the Routh Theorem. Routh Theorem is actually allowing us to assess convergence or divergence, or so basically assess dynamic stability of equilibrium without resorting to finding the roots of the characteristic equation. Here is the theorem. Let me just explain this to you step by step. Okay, so how does it go? The real parts of all the roots of the nth degree polynomial equation. So look, here we've got polynomial equation that we are encountering once we so this is our characteristic equation. However, remember that the case we are dealing with when we talk about differential equations is associated with A0 being always 1. So actually we could replace every A0 over here with 1. However, the theorem is more general. So even if we had characteristic equation with the coefficient next to the to r in the highest power, we still could use it. So let's keep it this way. Just remember that for our purposes, A0 is always 1. Okay, so definitely we know that this theorem deals with a nth degree polynomial. Now look, before we move further, I just want to put your attention into this. The real parts of all the roots. What does it mean, real parts? Look, of course, when we were dealing with differential equations, we had real roots, but we could have either real distinct roots. So we would have negative a1 plus minus square root out of a1 squared minus 4a2 over 2, right? And this, of course, is a real number. Of course, because we are assuming a1 squared is bigger than 4a2. Then we have a case of repeated real roots, right? So we written that we have R3 equal to R4, and they were both equal to negative A1 over 2, because in this particular case, this holds true, which of course, this part disappears, and we've got just this. This is a real number. However, when we're talking about complex roots, our solution looked a little bit different. We had plus, minus, and then we divided into two expressions. And we had 4a2 minus a1 squared I over 2. Right? And in this case, where we have that a1 squared is lower than 4a2, we have complex roots, right? And look, we were always saying that this complex root can be written as h plus minus vi, right? That is our h, and that is our v, right? Now, this is a complex number, and we were saying that this part of a complex number is an imaginary part, while this is the real part. And look, when we were dealing with complementary function under complex roots, we got that this is the expression that we had was e to the power ht times a5 cosine vt plus a6 sine vt. And look, we know that this is a circular function, and the convergence actually does not depend on this part. It just depends on the sign of h. Sign of h needs to be negative. So look, in this case, in the first case, in two real distinct roots, if we want to have convergence, both of these roots need to be negative. If we have repeated real roots, this repeated real root needs to be negative. And finally, in the case of complex roots, the real part of the complex roots, conjugate complex roots, needs to be negative. So look, actually this is what we get from the Routh theorem. Look, the real parts of all the roots. Look, in real part, in the first two cases are just the full roots. However, in the case of complex roots, the real part is h. And this is what the theorem is talking about. So R1, R2, R3, R4, and H from R5 and R6. Right? So we are sure that what we are talking about here is what is interesting to us from the perspective of assessment of convergence in the context of differential equations. Okay, so let's move on. The real parts of all the roots of the nth degree polynomial equation in this form are negative. Negative is what we want, right? In each case, negativity is allows us to say we've got dynamically stable equilibrium. And look, another important part here is if and only if. Are negative if and only if. Which means that if this condition that follows is not met, we can't be 100% sure it's going to be divergent, because at least one of the real parts of the roots is going to be positive, which guarantees us divergence for given differential equations. Okay, so we know that they're all negative if and only if the first n of the following sequences of determinants, n of course refers to the degree of the polynomial, right? So we are only interested in the first n of the following sequences. And look, these sequences go like this. Determinant first is just A1, very easy. Then 2 by 2, we go from A1 we go to A0. Then in the next column we've got A3 and we go down A2. And now look, we will have A1, A0, 0. Then we go to another odd number, A3, and we just go down, A2, A1. A5, which is next odd number, then A4, A3. And we repeat this as many times as we need. Look, if degree of the polynomial would be 5, we would need 1, 2, 3, 4, 5 determinants. If degree would be 9, we would need 9. And finally, so sequence of determinants are all positive. What does it mean is that we need to calculate all those determinants, and the condition for us to be sure that all the real parts of the roots are negative is that all these determinants in a sequence are negative. Okay, and look, here we've got one more thing. AM equals to 0 for m higher than 0. Okay, let's just say that we are dealing with polynomial of degree 5. Here, we need to calculate 5 different determinants, right? Because n is 5. We always calculate n first of the following sequences of determinants. But look, here we will have A7, A6, A8, A9, but m, of course, in this case, in their cases, oh, it's not bigger than 0, it's bigger than n. Here, m over here is bigger than n. So instead of A6, I will write 0, A7, 0, A9, 0, 0, 0, 0, and only elements with A5 would be the last to enter over here, and the rest we would fill with zeros. Everything above n equals 5. Okay, look, let's just do a very simple example, and I think that this theorem will become very clear to you. Okay, so what do we do over here? Okay, give me a second. So, let's just say that we need to assess dynamic stability of equilibrium for the following equation. Plus 6 plus 14 plus 16 y prime plus 8 y equals to 24. Actually, this is the equation we already dealt with in the previous video. We know that it has all negative real parts of all of its roots. So we know we should have convergence. But as I told you, we needed to go through I needed to calculate a lot before I was able to solve the characteristic equation, which is very complex in this case. However, look, we can clearly, even without finding characteristic equation, deal with the same issues using the Routh Theorem. Because look, what is our A0 going to be? Well, our A0 is always 1, because here we have coefficient 1. Then A1 is 6, right? A2 is 14, A3 is 16, and A4 is 8. Okay, now, what is the degree of our polynomial in here? Well, it's 4, right? Because the highest derivative, degree of the derivative, is 4. Okay, which means we will have to calculate 4 matrices, determinants, I'm sorry. Okay, so first one is just A1. In our case, it's 6. Determinant of 6 is 6. It's definitely positive. Okay, now we construct the second one. How do we start? A1, and now we go for lower. A0, which is 1. Then we go to another odd index, which is A3, which is 16. And below we've got A2, which is 14. This determinant is equal to 68. Again, a positive outcome, which is what we want. Okay, then we need to do the third determinant. Okay, so we start with A1, which is 6. We go to A0, which is 1. And then we have just 0. Okay, now we go to A3, which is 16. A2, which is 14. A1, which is 6. Okay, and now, look, now we should have A5. But we do not have A5. When we say AM is equal to 0 for m bigger than n, it's 0. Then we have A4, which is 8, and A3, which is 16. Now, if we calculate this determinant, we will get 800, which is again bigger than 0, what we want. And now, finally, we need to calculate the last determinant. So again, we start with A1, which is 6, then A0, which is 1, and then we will have 2 zeros. Then we will go to A3, right, 16, and we go down. A2, A3, which is 16, A2, which is 14, then we've got 6 and 1. Okay, now we should have A5, which we don't have, so we put 0, and then we've got A4, A3, A2. Then we should have A7, again 0. A6, 0, and A5, 0, and then we've got A4, which is 8. And look, the more zeros, you should remember that zeros are your ally when you calculate determinants. So, of course, the more zeros, the better. And finally, if we calculate this determinant, it turns out it's equal to 6,400, which is again bigger than 0. And because those 4 determinants are bigger than 0, it means that we've got convergence and dynamic stability of equilibrium. Okay, and look, this, as you see, using the Routh theorem, we didn't even have to find the actual roots. We just know the real parts are going to be negative, and because of that, we can be certain that if enough time passes, complementary function goes back to particular integral, so to the equilibrium level. Okay, so with this theorem, Routh theorem, we've actually finished the topic of differential equations. But we're not going to forget about it. We're going to build up upon it. Look, as I showed you here different cases and how they lead to equilibrium, especially it was seeing how important those new cases are when we were modeling GDP. And we saw how very simple differential differential equations can actually give us a GDP time path that is characterized by both linear trend associated with long-run growth of the economy and fluctuations around equilibrium, which we attribute to business cycles. However, look, GDP is not measured at every moment in time. It's usually annually and quarterly. If you're lucky, in case of some countries, but usually this is only done for industrial production, you get data on monthly GDP. But this is, as I said, this is mostly for industrial production, so this is not for the entire economy. But in those cases, we will not have value of GDP for every moment in time. You will have only at certain periods of time, like quarters or years. In this case, what we do with differential equations is not fully applicable to analyzing a situation that we call discrete time. I hope you remember this from dynamic economic analysis. Here we were dealing with continuous time. So we knew what is happening at every moment, every second, every millisecond, every nanosecond. But what if we know what happens only once a year or once a quarter? It turns out that we can take everything that we learn about differential equations, modify it slightly, and get even more realistic tools to deal with the problems of discrete time. And this is what we're gonna do since next week and next video. We're gonna move to discrete time, which means that instead of dealing with differential equations, we will be dealing with difference equations. But don't worry, everything you learn about differential equations will be extremely useful, because as you will see, if you understand this, understanding how difference equations work is just one step away. Okay, thank you for your attention and see you in the next video. Take care.